Alright, so we're going to talk about this thing called a logistic function. Alright, I'll go ahead and point out that a logistic function has this general equation. You're going to want to write that down. Okay, and a logistic function looks like this. It has two horizontal asymptotes. So it has this horizontal asymptote up top, y equals c, and then it has another horizontal asymptote down here, usually at 0, or the x-axis. Okay. Logistic functions are really helpful for modeling things like population growth, growth of, say, a virus, or even growth of a rumor. So for instance, the reason why logistics functions are so helpful is that an exponential function would look like this. So to an exponential function, to start off looking about the same as a logistic function, but then it keeps going up. That should be an exponential function. Okay. The problem with an exponential function is that going up to infinity doesn't fit most things in real life. So for instance, let's say that I was trying to spread a rumor around our school that we were going to change our mascot to the turtles. So we're not going to be dolphins anymore, we're going to be the turtles. And I was trying to spread this rumor. And so let's say that I started this rumor. So this rumor started with a grand total of one person. So that value would be 1. And I spread it to all of my students, and they believed it and spread it to their friends. And so after a while, my rumor slowly started to spread until it got to a certain point where it was starting to spread very quickly. Okay? At this point, about half the school had heard my rumor, and it's starting to spread quickly. But as I move along this trend line, okay, my rumor is starting to spread at a slower and slower rate. And the reason why is, ultimately, I'm starting to get to a point where everyone in the school has heard this rumor. Well, y equals c. In this case, c would be the school's population. Because, obviously, my thing has to fade out. Once my rumor spreads to the entire school's population, it cannot grow anymore. So that would be an example of why I would want to use a logistic formula. If I tried to model that using exponential, then once I got to this point right here, I would suddenly have more people hearing my rumor than actually are at the school. Alright, so that's an example of where logistic is helpful. Logistic is also helpful for spread of viruses. So let's say instead of a rumor, we were talking about the spread of the flu. We had a recent spread of the flu at Battery Creek. We're still unfortunately not done with it. So my spread of the flu would be, well, how many people got the flu initially? Let's say we had a small number. Let's say like 6 different people kind of initially had the flu. They got it from wherever they may have gotten it. And then the flu started to spread slowly. But then at one point in time, we had maybe not half the population of the school, but quite a few people had gotten the flu, and it seemed like everybody was dropping. People were dropping like flies with the flu. But as we move along, we are probably somewhere up in this area, because now the amount of people getting the flu is starting to slow down. Now, hopefully this line right here is not actually going to be the entire school's population, because that would mean that everyone gets the flu. Hopefully that line is beneath the school's population. But the point is that it's ultimately going to approach a value that it's not going to go above. There's going to a certain number of people who are going to get the flu at Battery Creek this year, and it cannot go past. Exponential would say, oh, it goes to infinity. An infinite number of people at Battery Creek get the flu, and that's not possible. A third way I can model this is population. So again, sticking with Battery Creek, we can model this by saying, oh, the growth of Battery Creek as a school. Well, Battery Creek started as a school at some point, and we can say we can use this to model wherever. I have no idea what Battery Creek's population was. We'll say 500 students. We can say that it started off slow, it grew quicker, and then it settled out. And this value right here just suddenly becomes very interesting, because that line becomes whatever our maximum population is. Well, in my first two examples, the max population was pretty obvious. It was either how many people were in the school or maybe a number below how many people were in the school. But when you're trying to use this to model the actual population, that line becomes very helpful because that gives me, well, what is the maximum population of our school? And I don't have to use this for school. I could use it for cities or states. I could model the population change in a city or a state and then use this to predict what that maximum population of that city or state is. And obviously that line can change as technology increases. That line can shift up because suddenly more people can live in a city or a state, okay? But for the most part, that line's very helpful in telling me what a maximum population is. So what we're going to do is we're going to use a problem. Oops. Sorry. There we go. So we're going to use the back of that paper, and we're going to do a problem. And I am going to specifically use New York, mainly because it's not one of your questions. So I'm going to white all this area out, and I'm going to look at New York. And this is referring to the state, not the city. So I took this, I'm taking this data right here, and I'm going to look at this. And I'm going to go to my calculator. We're going to go to Stat and Edit. And I've already put the New York values in. And notice what I put in for X. Instead of putting 1900, 1910, 1920, I used 1900 as year 0 and went 10, 20, 30, 40. And I realized that New York didn't start in 1900, but it makes it easier on my calculator when I do this if I'm using smaller values, especially if L1 and L2 are similar. So obviously 7.1 isn't 7.1 people, it is 7.3 in millions. So 7.3 is millions, 0 is actually the year 1900. And so as I go through my list, I keep going and I end up at year 100, which is 2000. Okay, so I put my data in, so my years in L1, my population of New York in L2, and then I'm going to go to Stat. I'm going to go over to Calc, and I'm going to come down to Logistic. It's option B. So I click on Logistic, and then this screen should look very familiar. It's the same as everything else when I do a regression. I'm going to go down to Calc. It's going to think about it. It's probably going to think longer than it normally does because logistics are a little more difficult to come up with. And it comes up with this equation. Okay, so the general form is y equals c over 1 plus a e to the negative bx. So that means my equation is y equals 19.87494,633 over 1 plus 1.75027 around the 7 e to the negative 0.035. The next couple digits are zeros, so I just stop there. X. Okay, so there's my regression formula, my logistic regression formula for the population of New York. Now, I can do a couple things with this. I can determine the max population of the state of New York. The max population as estimated by mine is this number right here. The max population would be 19.87 million people. So if my logistic formula is true, then the state of New York will cap at about 19,087 million. Okay? I can then also use this to predict, well, how many people is going to be there at a certain time. Well, I happen to know that the last census in the state of New York was in 2015. Okay, So at 2015, we know exactly how many people are in the state of New York. More recent than that are just guesses. So we're going to plug 2015 in for X and see how close my logistic model fits. Well, to do that, I need to remember that I used the year 1900 as year 0. So that means the year 2015 is going to be 115. So I'm going to come over to my calculator. And I went ahead and have it typed in, so I will scroll through here so you can see exactly what I have typed in though. So I typed in the 19.8 divided by, and then put the denominator in parentheses. So 1 plus, and then the 1.75 e to the negative, and then put 115 in there, and hit enter. And so my estimate for the population of New York in 2015 was 19.27 million. Okay, so that was the max population, and that was my estimate for the year 2000. Well, the year 2000 is already passed, so I can go back and actually check and see, well, let's see how close we really were. Alright, so this right here is an estimate for right now, but if you notice down here it says in 2000 that was the population of New York, 19.7 million. So my estimate was a good bit below the actual, okay? And the reason mine was off is because our data set was fairly small. We didn't necessarily have a lot of data, and we didn't have any data since the year 2000. So if we had more data, we'd probably gotten a more accurate prediction. But notice this. This is a map of the population growth of New York. Notice it started off really flat. Okay. As I move along, it starts increasing. I get right about here in the early 1900s, and I have very fast population growth. But notice that starting at about the year 2000, that population growth has started to decrease. Okay, so it's still increasing each year, but it's increasing at less and less of a rate. Okay, I can look over here at this map and it tells me exactly the growth rate is decreasing. Okay, so whereas in the early 1900s my growth rate was about 1.9, now my growth rate is like 0.1%. Okay, so I see that this actually does follow a logistic function. I have that flat, starts decreasing, and then it's going to start flattening out as time goes on. Okay. Well, what if I would have tried to do this using exponential? So I'm going to go back to our problem. And we're going to do the same problem using an exponential. Okay. So I'm going to pull out my calculator again. I'm going to go stat. I already have the data in edit, okay, because I'm going to use the same data. So I'm going to go over to calc, but instead of using logistic, I'm going to use EXP, or exponential regression. Go down to calculate. Just going to think about it for a second, and it gives me that. So if I look at this, my general form is y equals a times b to the x, which is what we saw on Friday. We were doing this. That's our general form for an exponential function. It tells me that a is 8.662 around the 1, and b is 1.009. We'll go 2. Now, I'm not putting a whole lot of decimal places there, and that is going to throw off my answer. Okay, the more decimal places I put in there, the more precise I get to my example. So And you're doing this, make sure you put all your decimal places in there. I'm just doing this one just for example though. So I'm going to say, okay, I want to predict what is the population in 2015. So I'm going to say parentheses 8.6621 and then parentheses 1.0092 and x. Okay. Oh, no, and not x. And then I'm going to plug in 115 graph. No, sorry. Wow. We'll hit enter. There we go. And I get 24.8. Notice a lot larger. So this tells me that in the year 2015, the population would be 24.83 million. So that's if I use exponential. Well, a reminder, that's 24.8. The actual value, let's scroll back up. The actual value is 19.7. So that logistic model we did where I was at like 19.2 is now looking very precise compared to 24.8. Okay, so logistic typically work better. Logistic will definitely work better over long periods of time. So exponential might work better for a specific date and time, but logistic does a better job of modeling population over an extended period of time because exponential assumes that I can go up to infinity and that I'm constantly growing, and that's not possible. I cannot get an infinite number of people to even fit in the state of New York. It's going to have to kind of flatten out over time. Alright, so see if you can answer the questions on that page using the data sets I gave you.